Have you ever stared at a huge exam question and just had no idea where to even start? Well, today, we're going to tackle a real beast, a 17-mark GCSE Chemistry question from AQA. It tests, well, pretty much everything, from basic chemistry to graph skills and data analysis. So, let's dive right in and break it down, bit by bit, using the official mark scheme to figure out exactly how to nail every single one of those marks.
So here's the setup. We've got sodium thiosulfate and hydrochloric acid reacting. As they do, the mixture gets cloudy, and that blocks light from getting to a sensor. Now, our goal today isn't just to get the right answer. Nope, we're going to learn to think like an examiner, to really understand the why behind every point. Let's get to it.
Here's our game plan for today. We'll kick things off with the basics of the reaction, then we'll get into the tricky stuff, like calculating rates with tangents. After that, we'll predict how the reaction changes under new conditions, take a look at the experimental method, and wrap it all up with one final data calculation.
Okay, first up, a nice, simple one-mark question. But don't underestimate it. It really lays the foundation for everything that's about to follow. It's all about one simple observation.
So the exam paper tells us that sulfur is produced. But that's not the whole story, is it? Why does making sulfur turn the solution cloudy? What's the specific chemical property they're actually testing you on here?
So what are the examiners really looking for? To get that mark, you've got to say that the sulfur is a precipitate, or a solid. Or you could say it's an insoluble substance. See, this proves you understand why it's cloudy. Just saying sulfur is made isn't enough. You have to describe its physical state.
All right, let's move on. And you know what? The difficulty is about to ramp up. This next part is worth a hefty 5 marks. And it's going to require us to read a graph and calculate a reaction rate at a very specific moment in time.
You see that phrase right there? At 30 seconds? That's the key. The rate isn't the same throughout the whole reaction. It's always changing. So how on earth do you find the rate at just one single instant? Well, for that, we need to use the graph they gave us.
This graph basically shows us the speed of the reaction, which is just the steepness of the curve. You can see how it's super fast at the beginning, right? And then it starts to slow down. To find the rate at one specific moment, like 30 seconds, we need to draw what's called a tangent. It's just a straight line that perfectly touches the curve at that single point without crossing it. Let's see how it works.
The mark scheme breaks this down perfectly. It's a really clear process. First, you get a mark just for drawing the tangent correctly at the 30-second mark. Easy. Next, you calculate the gradient of your tangent line, not the curve itself. Then, finally, you get a mark for converting that number using the factor they give you in the question. If you just follow these steps, all 5 marks are yours.
This next question is basically asking us to explain the shape of the curve we were just working with. Why does it start off so steep and then gradually level out? This is a really fundamental idea when it comes to reaction rates. And the mark scheme lays it out plain and simple. For 2 marks, you need 2 linked ideas. First, you just state the obvious. The rate decreases. Second, you explain why. The concentration of the reactants goes down because they're being used up, right? Fewer particles means fewer successful collisions per second, and that means a slower rate.
Okay, so we've analyzed the curve. Now it's time to predict how it might change. This next bit tests our understanding of what's really controlling the reaction.
We're back to our graph. Just take a look. See how it goes completely flat after about 80 seconds? Why do you think that happens? And what would the curve look like if we, say, doubled the concentration of the sodium thiosulfide? That horizontal line means the amount of light getting through isn't changing anymore. In chemistry terms, that means no more sulfur is being made. So what happened to our ingredients? Now here is where being specific is everything. The mark scheme is crystal clear. You have to say that the hydrochloric acid is the one that got all used up. It's what we call the limiting reactant. It's the ingredient that runs out first and brings the whole show to a stop. Just saying the reactants were used up is way too vague. You won't get the mark for that.
Okay, prediction time. We're doubling the concentration of the reactant that we had plenty of. How is that going to change the shape of our curve? This is a classic 2-mark sketch question.
So the mark scheme is looking for 2 very specific things. First, your new line has to be steeper at the beginning. Why? Well, a higher concentration means a faster initial reaction. Makes sense. Second, it has to level off at the exact same percentage of light, 24%. And why is that? Because the amount of hydrochloric acid, our limiting reactant, is still the same. So we'll make the same total amount of sulfur and the reaction stops at the same point.
All right, time to put on our imaginary lab coats. This section shifts away from the theory and gets into the nitty-gritty of how you actually do the experiment, and some key scientific words.
These are 2 quick and easy marks.
To improve the method, you always want to control your variables better, so blocking out other light sources is the right answer. And the special term for getting similar results yourself is repeatable. You might have heard reproducible. That's when someone else can follow your method and get the same results. It's a small difference, but a really important one.
We are on the home stretch now. This final part of the question is worth 4 marks, and it asks us to analyze a totally new graph to figure out a relationship and a chemical ratio.
This last graph shows us how much of each reactant you need to make a certain amount of sulfur. Just take a second to look at the axes and the 2 different lines. The key to cracking this is just careful reading.
The last 2 questions are tied together.
First, what's the mathematical pattern you see with those straight lines going through the origin? And second, can we use this graph to work out the reacting volume ratio for our 2 solutions?
And here is exactly how the mark scheme expects us to figure this out. That straight line through the origin means the volume is directly proportional to the mass. For the ratio, all you do is pick any mass of sulfur. Let's make it easy and say 0.20 grams, and then read the volumes you need from the graph. You'll see you need 50 cubic centimeters of sodium thiosulfate and 200 of hydrochloric acid. And the simplest whole number ratio of 50 to 200, it's 1 to 4. And just like that, you've got the final 3 marks.
So what's the big takeaway here? Breaking down a question with the mark scheme in hand shows you that it's not some secret code book. It's actually a blueprint for how to think like a scientist. It rewards clear, logical steps and precise language. And if you can learn to think the way it's structured, you're not just learning to pass an exam. You're learning how to communicate science. And believe me, that's a skill worth way more than any mark.